Good morning to all of you.
Good morning.
So, are there any questions, doubts? Anybody? Any question, doubt? Whatever we discussed in last class or earlier classes? Okay, so then if there are no questions, let me start. So I'm going to continue with the contact mechanics. It's not right. Is my screen visible?
Yes, sir.
Okay. Yeah, so then let me start. So we are continuing with the contact mechanics. So last class we did the element level governing equations based on Lagrange multiplier approach, and today I am going to develop the element level governing equations based on penalty approach. So element level governing equations penalty approach, and we are going to be consider the same assumptions which we considered in the last class. That is, I am not considering finite deformation, so we are saying that the small deformation and linear elastic, the bodies individually, the target and contactor bodies are linear elastic. So first let's look at the big form. Say for the, so big form is actually the same, only thing is the contact force we are going to express using penalty approach. So let me write anyway. So the for the target, the big form as we wrote in the last class, so integration over volume of the target, so delta epsilon for the target into sigma t dv, and this is equal to virtual work of body forces, tractions, and the contact force. So integration over Vt delta Ut transpose into Fb in the target. So this term plus the integration over area where the traction on the target is acting, and delta Ut transpose into traction in the target dA, and minus we have this work done, the virtual work of contact force, so integration over the contact area. So the same assumption, we are assuming that the contact is frictionless, so tangential traction is a null vector. So delta U and T transpose into FNDA. So now in the penalty approach, what we are doing, so I have already said over here. So we are actually kind of going to make use of this condition whether there is a gap between the bodies or no, there is a interpenetration. So in the penalty approach, Fn will be equal to 0 if G was gap. No, you remember, if G equal to 0, we have already talked about how to calculate G. So we take a point, one point on the contactor body and then find out the corresponding point on the target body, and then take the vector from that point on the target body to the contactor point, point on the contactor body, and take its dot product with nt. That gives you G. So if that G is greater than 0, then that means there is a gap. So actually the bodies are not in contact, so the contact force would be actually equal to 0. So of course this condition has to be checked. No, the G has to be calculated, and then this condition has to be checked. And now this will be equal to penalty parameter, say Kp. Kp is the penalty parameter into unt minus unc. This is actually interpenetration. As you remember, we have defined this as unt minus unc as the interpenetration, the displacement of the point on the target body along the normal minus displacement of the point on the contactor body along the common normal. So this is interpenetration. So then the Fn is equal to this if yeah, if G is less than equal to 0, where G is gap. And no, you can refer to the lecture where we have given this how to calculate gap. So of course then you have to know, you can see this gap would be just the reverse of interpenetration. So unt minus unc is the interpenetration. So unc minus unt in this case would be actually G, gap. So this is how we are going to do. So already if you see, it's kind of an iterative problem because we have to find the gap, and if gap is 0, we take Fn and solve the problem, and then again find the gap. Or if gap is less than equal to 0, then we find this Fn and solve the problem, and then again update it. So it's kind of an iterative problem. So it has to be I know it's not a single solution. So problem is already a nonlinear. The contact is a nonlinear problem, as you see over here. So when you have seen, of course, in the Lagrange multiplier approach, we have said that there is a inequality, so that also would convert the problem to a nonlinear problem in the solution when you solve. And you would see that for solving the contact problems, actually you'll have to use the constraint optimize, whatever techniques we learn in constraint optimization. So those constraint optimization techniques are actually all useful over here. So in this penalty, of course, I have also earlier introduced the max function. I'm not using that here. I'm explicitly saying that if gap is 0, greater than 0, then Fn is 0. And if gap is less than 0, then the gap Fn is given by this. So you have to go by this condition, to calculate the normal force, at the contact point. So now we want to develop the element level governing equation. So we again these terms are standard, as you know, in the standard FEM how to convert this to the in the form of stiffness matrix, in the form of load vector due to body forces, load vector due to traction forces. So we are again, I know this is a special term, so we are going to look at how to handle this term. So now let us consider this term, last term, what I have written here in the big form. So that is minus integration over the contact area, and then we have delta unt transpose into Fn. And FNB, of course, if it is 0, then that term is anyway going to be 0. So we are taking the case where G is less than 0, so that Fn is non-zero. So now we have delta UNT transpose into Fn, and Fn we have written the Kp into UNT minus UNC, UNT minus UNC dA. And yeah, here if you look at, no, this where G is gap and Kp is penalty parameter. And for enforcing the constraints accurately, this penalty parameter has to be a large number. So this is a large number. So now actually when you choose this parameter, so when you say large, how large actually, so if it is very large, it leads to ill conditioning of the stiffness matrix, so you can't solve. If it is too small, it will not enforce the constraints at the contact region accurately. So it has to be, appropriate value. Theoretically, of course, to enforce the constraints at the contact region accurately, this has to be infinitely large. But yeah, we cannot work with that, so we work with a certain range of values. And usually, we get whatever stiffness matrix we get from here, we take the maximum diagonal element in that, and maybe 1,000 times of that maximum diagonal element in this stiffness matrix, whatever we get, we take the Kp penalty parameter, and that usually works well. So that is how you go with this. So now if you look at this term, so I can write this term as minus integration over the cross sectional area. Slightly rewriting this. So UNT transpose, and then we have this KP, and UNT and UNC, because I'm going to put in the form of matrix vector products. So I'm rewriting this slightly. So I'm putting here this as one row vector as 1 1, and then as a column vector as UNT and U minus UNC dA. So it will give you the same thing what we have written over here, as you see over here. So when you multiply this 1 1 into UNT minus UNC vector, you will get the same thing. So now we have already seen that how we define this displacement along normal to the target body. So that was transpose of normal to the target body. So NT transpose, this is normal to the target body, it's transpose we are taking, and then the displacement of the target body, and this can be written as NT transpose, and this UT we are writing as the interpolation matrix N into vector of elemental degrees of freedom for the target element. So that is dt. So you know that is how we are writing. Now if you look at this minus UNC, that's another term we have over here. So that will be equal to actually, as per definition, minus NT transpose into UC, and you see this minus NT is actually equal to NC, normal to the contactor body, so we can write it as NC transpose and into UC, and UC is can be written as interpolation matrix N into a vector of elemental degrees of freedom for the contactor body, so that is DC. And we have delta UNT over here for the target body. So you can see that delta UNT can be written as basically this NT transpose from this equation into N into delta of dt. And now if you look at, we have this term over here. So that term we can write as UNT minus UNC. So this can be written as, you can write in terms of the, we'll have to combine the elemental degrees of freedom for the target as well as the contactor bodies. So UNT of course is equal to this NT transpose into N, and then we are combining the degrees of freedom. So here I am putting a null vector and then writing here the degrees of freedom of both target as well as the contactor elements. So this is unt is no, when you multiply it simply becomes nt transpose into n into dt, because this is a null vector, so null vector into dc will be a null no, null matrix into vector dc will be a null vector. And for unc you can see that minus unc we have written over here as nc transpose into ndc, so we can put here a null matrix, and then here we will have nc transpose into n, and that will give you basically this unt minus unc vector, which is coming no, in the definition of normal force at the contact location. So now if we look at no, this term, the last term which we have, so this one, this integral term, so if we look at that, so we'll have minus integration over the contact area, and then the penalty parameter kp. Kp is a scalar, so you can write it anywhere. And then we have delta unt transpose, and delta unt is given by this. So from this one you write delta unt transpose, so that would be delta dt transpose into n transpose into nt, because nt transpose transpose will become simply nt. So you will have delta of dt transpose into n transpose into nt, that's what we have. And then here kp I have already written, then this vector 1 1 is there, and then we have unt minus unc vector that is given by this. So if you write this, you have this nt transpose into n and a null matrix, and then a null matrix, and nc transpose into n matrix, and then we have here dt and dc da. Yeah, so if you have no any doubt in any of the steps, no, you can stop and ask. So now if you would see that this can be written as minus, and this variation of vector of elemental degrees of freedom can be taken out of the integration sign. So you can write this as minus delta dt transpose, that can be written outside the integration sign, and then we have this matrix integration over AC, and then we have this parameter, no, you see kp. And then now what I'm going to do is we have of course this n transpose into nt, so this is there. And now see, we can multiply this and this, these two if we multiply, so we will have here no 1 1, so we will multiply, we will get nt transpose into n, so 1 into this and then 1 into null matrix, that would be null, uh, contribution, so this is what we will get. And when we multiply now this with the second row, this particular row, so we will get basically this nc transpose, this is the first column, and this nc transpose, this is the second column. So let me put some space rather than writing them very close by. So this will be nc transpose into n matrix and into dA, the vector of elemental degrees of freedom we are taking out of the integration sign, and then here we will have this dt and dc. So now this can be written as minus delta dt transpose, and let me slightly rewrite this. So integration over AC, and we have this kp. And now what we can do is now multiply this, take it inside this term inside this. So then you can write this actually as kp into this n transpose into nt, and into then we have this nt transpose and into n. So that's the first term we will have. The second term we will have this n transpose into nt, and then we will have this nc transpose into n and da. and then we have here of course this dt dc, that vector you have. And so what we can actually do is we can give the names to these matrices. So these are the contact stiffness matrices coming from the penalty term. So we can write this as delta of dt transpose, and the first matrix, that is kp into this integration over ac. We can say that this is involving both normal to the target, as you see. So we can say that's the contact stiffness of the target no interaction. As you see, that term is coming over there, and here you see the target and contact is coming. So we can say this is a matrix, and this is also a matrix, contact matrix. Target and contactor are coming into picture. So we can write it like this into dt and dc. So if you see over here, so where kctt is basically integration over the contact area, and then kp n transpose into nt into nt transpose into nda. So this is k, and similarly we have kctc, contact stiffness, that's also contact stiffness but involving the target and contactor both. So integration over contact area kp into, we have the n transpose into nt, and then we have nc transpose into nda. So once we Rakesh, right now I'm having class. So now we can write the element level governing equation. So now we write the element level governing equation for target. So the other terms, no, I think I hope, no, if you have a difficulty in actually writing element level form for these, you can let me know. But I understand, assume that no, you can write easily for these, and that's why I'm explaining only about this term, how to write this term. And therefore finally from the big form you get the element level governing equation for the target. So you would see that the element level governing equation for target is now first term, know that will give you the stiffness matrix of the target element. So that is kt, this matrix kt. I think, let me not put the, because I'm already putting that double bracket into, we will have dt plus, now this term we are taking to the left hand side. So there is a minus sign. When we take to the left hand side, it becomes plus. So we will have this term as plus. No, we have these two matrices kctt, and we have this kctc, and this is multiplied with these two vectors dt and dc, the vector of elemental degrees of freedom of the target element and the corresponding contactor element, and this will be equal to the load vectors due to body forces and traction. So that we are writing as fb for the target element level governing equation, plus we have the ft for the target element level governing equation. So now if you look at here, I have already defined these matrices. So these are already defined. So this is the element level governing equation for the target element. So where now this, if you look at this kt, so this is integration over volume of the target body, and that would be b matrix. So b matrix transpose into constitutive matrix c into b into dv. So where the c is, this is constitutive matrix for the target body, and this afb TE is equal to integration over volume of the target body, and then we have this N transpose into FB for the target into dV, and this FT for the target element level Gauni equation is integration over the area of the target where the traction is acting. So this is equal to N transpose into TT TA. So we have already defined all other quantities, so you know how to. So this is the element level Gauni equation you get for the target body. Now coming to element level Gauni equation for the contactor body, approach is actually same. Element level governing equation for contactor body. So first let me write the virtual work. So the virtual work of the stresses. So that is delta of epsilon for the contactor body. It's transposed, right? No, both is strain as well as stress are written in the vector form, 6 by 1 vector. So this is sigma c dv. So this is the virtual work of stress. It is equal to virtual work of externally applied forces. So here we are saying Vc, and then we have delta Uc transpose into body forces in the contactor dv, plus we have the integration over area where traction is acting on the contactor body. So we have delta Uc transpose into TCDA, and then we have the virtual work of contact normal force. So that is plus now here in the contactor body integration over AC. I have already explained you why plus and minus in the target and contactor bodies in the previous lecture. So delta UNC transpose into FNDA. So this is the virtual work. Now because we are working with the penalty, so we already know that Fn equal to 0 if G is greater than 0, and Fn equal to Kp into interpenetration, which is UNT minus UNC. This is interpenetration. Now if G is less than equal to 0. So you already know Kp is a penalty parameter. And so now we have to look at the last term. The other terms, again, as I already said, you know how to write. So I will just discuss about how to rewrite this last term in the virtual work what we have. So that's the integration over the contact area delta UNC transpose into FNDA. This can be written as integration over AC delta UNC transpose, and Fn can be written as Kp, and then I'm introducing the same this vector 1 1, and then into UNT minus UNC dA. So now we have already introduced I think most of the quantities. So we have introduced UNT already, we have introduced UNC also, but because I need the variation of UNC, so let me write that. So UNC is nothing but we are defining with respect to normal to the target body, that you should be very careful, into T into UC displacement vector of the contactor body. So this is equal to NT can be written as minus NC, so we will have minus NC transpose into UC, and UC can be written as N into DC, so we will have minus NC transpose into N into DC. So therefore delta UNC, if you look at, will be minus NC transpose into N into delta DC, because that's the unknown vector of elemental degrees of freedom for the contactor element. So we take the variation of that. So once we have this, so then if you look at this term, I can write as this term can be written as minus integration over, now why minus is coming, because delta unc has a minus sign, so that is why that minus is coming. So we will have minus integration over AC, and then delta UNC transpose. If you look at delta UNC transpose, so that would be delta DC transpose into N transpose into NC transpose. Transpose becomes no, just the NC and with a minus sign. So we will have here delta DC transpose into N transpose into, we have this NC, and then we have no here KP, and then this vector 1 1, and then we have already written this UNT vector UNT minus UNC. So if you are we are just making use of the same thing what we have written over here. Now if you see this UNT minus UNC, so we are taking that same vector. So we have this vector as this NT transpose into N, a null matrix, and then we have NC transpose into N dt and dc dA. So now if you look at this, can be written as, we can take delta dc a common, you can multiply this N transpose into NC. First you can multiply this, and then multiply NT transpose NC inside. So these steps are same what we discussed already. So you can finally write that minus and delta DC taken out of the integration sign. So then we have this matrix integration over AC, and then let me write KP over here, and then inside what you're going to get is this N transpose into NC, and then here we will have this NT transpose into N. That's the first one. The second one would be this N transpose into NC, and then we have this NC transpose over there, and then this N, and then we have DA, and then we have this DT and DC. So now we can write this as minus delta DC transpose. This first matrix, if you look at, it is NC into NT transpose. So let me denote that by KC between C and T. This is contactor and this is the target. So this is CT, and this is contactor and contactor. So KC CC, and then we have of course this DT and DC. So now here if you look at, so where we have KC, this stiffness CT is nothing but integration over the contact area KP into N transpose into, we have NC into NT transpose into NDA. So we have the same thing what we are defining here, and the KCC is integration over AC KP and N transpose into NC into NC transpose into NDA. So now once we have defined this, so you can actually write the element level governing equation. Now we are writing for the contactor. So the first term of the big form, ultimately you are taking variation of delta dt delta dc common out, because that is arbitrary. So what we have in the multiplication, that should be equal to 0. So this term gives you for the Kc into dc, and this term, because it has a minus sign, we take it to the left hand side, so it is getting added on the left hand side, and these two terms, after taking the variation delta dc out, we keep them in the right hand side. So from this, that is what you are getting, the eliminable Gaon equation for the contactor as this Kc into dc plus you have this Kc Ct, KCCC. This is this term, no, we are taking to the left hand side. So we will have dt dc, and is equal to this vector is force vector for the due to body forces for the contactor element label plus the force vector coming from the traction for the contactor body at element level. So yeah, this is what you have. So we have already defined these matrices. What is not defined, so we can say where you have this Kc is equal to integration over volume of the contactor body B transpose, this is strain displacement matrix, into this will be the constitutive matrix. C is the constitutive matrix for the contactor. The constitutive matrices for the target and contactor can actually be different. They could be of different material and things like that. Of course, both of them are be assuming as linear elastic, but the material could be different. So we have B into dV, so that's your stiffness matrix for the contactor element, and then we have this FBCE is equal to integration over the volume of contactor element. So we have N transpose into we have FB for the contactor into dV, and FTCE is equal to integration over area of the contactor body where traction is acting, and then we have this N transpose into T, the traction in the contactor body, dA. So yeah, this is the element level Gaon equation. So we have got one element level Gaon equation here, for, as you see, for the uh, target body and one for the contactor body. And you will actually to solve the problem, no, to satisfy the contact constraints accurately, we need a large value of penalty parameter. But if we at once, if we take a large value of penalty parameter, there are convergence issues. So in the solution, usually what is done is we start with a smaller value of penalty parameter, solve the problem, and then increase the penalty parameter, solve the problem again. So we do this in steps. Now to improve this, the convergence in this iterative process, it's a iterative even it would be iterative for every value of penalty parameter. So there is another method which is improves the convergence, that is known as the augmented Lagrange method. So the software, if you see, you will have option for using Lagrange approach, you will have option for penalty, you will have option for augmented Lagrange method, and there are few more methods, but these are most popular ones. So I will just briefly tell you what is done in augmented Lagrange method. So we have discussed Lagrange multiplier, we have discussed the penalty approach, and then augmented Lagrange method, what I'm going to discuss. The advantage in penalty method, you would see that there are no additional unknowns. Whereas in the Lagrange multiplier, you see that Fn, the contact force, is treated as an unknown. So there are additional number of unknowns, although the contact constraints can be accurately enforced in that. But you will see that there are additional basically the unknowns there, whereas in the penalty approach there are no additional unknowns, only the displacement, degrees of freedom of the target and contactor are there. But no, it involves penalty parameter, which can be a problematic if it is very large in conditioning, and therefore we cannot solve equation. If it is small, it will not enforce the contact constraints accurately. So then there is a thought process that why not to combine these two, Lagrange method and penalty, both can be combined together, and that is known as augmented Lagrange method. So it is augmented by penalty method. So augmented Lagrange method. So in this, what is done is basically no. Let me write the big form. So what is done is, this is basically, we do what we do is we combine penalty and Lagrange multiplier method. Lagrange multiplier, we have discussed in the last class. So that is what is done in the augmented Lagrange method. And this is also actually, we see all these are actually the constraint optimization techniques. So if you study optimization, you have Lagrange multiplier approach, and based on that, of course, you derive the first order necessary condition, what are known as Kuhn-Tucker conditions, KT conditions. So that you use penalty method also you use in the optimization. And of course in the penalty also there are a couple of variations, and you also use augmented Lagrange method in the optimization. So constraint optimization problem. So contact problem solving is like solving a constraint optimization problem. So in this case, when you look at the weak form, let me write just for the target, and no, you can extend the same thing the way we have discussed. You can extend it for other bodies. So for the target, let me write. So it will give you a basic idea. I'm not going into details, but just want to give you a basic idea. The approach is same. So now what we do is the integration over the target body delta. These terms are same. Epsilon transpose into sigma t dv. So this term is same, and we have is equal to integration over the target body delta u t transpose into body forces dv plus integration over the area where traction is acting. So we have delta ut transpose into traction. So we have this traction dA, and now see what we do is we add, we have the Lagrange multiplier term as well as we have the penalty term. So now we have two type of terms here through the contact. So integration over the contact area, and then we have delta unt transposed into this. Now a different, because we have to distinguish between the contact force. So one Fn is Lagrange multiplier, I'm putting as Fn bar. So we add this term Fn bar dA, and minus we add the integration over the contact delta unt transpose into Fn. This is the penalty term we are going to add. So I will just define this is Fn dA. Now here Fn. No, this is a Lagrange multiplier, which would be treated as an unknown. Although there is a slightly different way of finding out this unknown. I will just briefly explain about that. So that is Fn. So this is the Lagrange multiplier, and this comes. This is the contact force comes from the penalty. So this Fn is written as 0. The same thing. No, if gap G is equal to 0, and this is equal to Kp into interpenetration, which is unt minus unc. If G is less than equal to 0. So now you see this term is also there, Lagrange multiplier term is also there, the penalty term is also there. Now the similar thing you do for the target contactor body also. So the same thing, you will have here plus sign, and you will have UNC transpose Fn bar dA plus integration over AC UNC transpose into Fn dA, and Fn is defined in this manner. Now in this process, how the solution is done. So let me tell you briefly. What we will do is we choose the penalty parameter Kp as a set of values, set of increasing values. So we start with a smaller value because the convergence is easier for smaller values of Kp. So we will start with the smaller values, and sequentially we increase the values of Kp. And in the every step, Because no, when we look at the augmented Lagrange method in the optimization, so when we look at the Kuntakar first order necessary condition for optimization, so that tells you that no, this penalty parameter at kth iteration, not the penalty parameter is increased sequentially, with a larger value. So for kth iteration to increase penalty parameter kp, one iteration is for every, so let us say no, for every value of penalty parameter there would be iteration. So I am talking of iteration where the penalty parameter kp is increased. So for this, what we do, this Lagrange multiplier, Fn bar for the k plus one iteration is written as in terms of Lagrange multiplier in the previous iteration plus the penalty parameter for the the current, you can use the current value of kp, k plus 1 value, and into this unt minus unc. This is evaluated at known at the previous iteration, kth iteration. So like this, you express this fn bar, the Lagrange multiplier, which is coming over here. So based on this, we use this augmented Lagrange method, which is convergence wise is better. You get the better solution. Of course, there are two sets of iteration. One iteration is within the for each value of kp penalty parameter, and to be, yeah, it doesn't really make much difference. So here you can just have kpk, so that the whole thing is at the kth iteration, although you can use kpk plus 1 as well. So one iteration is that you are taking the set of increasing values of penalty parameter kp, and for each value of kp you will have to solve the problem iteratively because of this non-linearity which is involved over here because of this contact condition. So either the bodies may be contact or may not be contact, or may not be in contact. So that's a non-linear problem. So iteration for that is also needed within each kp value. So this is how you basically uh, formulate the contact problem. So I have given you some basic formulation. No, of course, when you are dealing with frictional contact, so you also have to look at the relation, the constitutive relation for the friction terms. So those kind, I know, of course, I have not discussed those kind of things. So, but you should be able to actually do that. So let me give you a problem. So you can try solving this problem. It's kind of a homework problem. So in this homework problem, what I am going to do is, let us say that we have a simpler problem. So this is x-axis, this is y-axis, and one element, I'm just talking of one target element and one contactor element. So this is node 1, node 2, node 3, 4 noded element, and node 4. And this is target T. And there is a another element which is contactor. So that element is, let us say, this is also a rectangular element. So node 5, 6, 7 and 8. This is contactor. So now if you look at the data, so node, and because you need the coordinates, node and x and y. At this particular instant, node is 1, so the 1 is coordinates are 0, 0. 2 is 1.5 and 0. 3 is 1.5 and 1. Units I am not mentioning, so can be any units. And 4 is 0 and 1. 5 is 0.5 and 1.5. 6 is 1.8 and 2.25. 7 is 1.3 and 3.11, and 8 is 0 and 2.36. So these are the coordinates. What you have to do is, for a point located at, so let us take some point at the center over here. So for a point located at the center of contactor segment, contactor segment 5-6, determine its contact point on the target line, determine the potential contact point in the target line 4-3. Also compute gap G. So yeah, you can try solving this problem. You can actually, you can also think of, if point 0.5 is touching 4-3, then for this case just point 0.5 is touching 4-3, how to establish the contact stiffnesses in the Lagrange multiplier approach, and how to establish the contact stiffnesses for in case of the penalty approach. So you can also think, also look at solving that. So I think this is where I want to stop. If you have any doubts and questions, now you can ask. Yeah, so that, yes, now if you have any doubts and questions, now you can ask. Yeah,
Hello,
anybody,
sir.
any question? Yeah.
Sir, I have a doubt regarding the initial contact. Like we'll be establishing, like if for target and contractor, if you're applying like some force and they're
Yeah.
coming in contact, so how to find that initial contact force, like to start the problem in the iterative process?
No, see, in case of Lagrange multiplier, you see the contact force is taken as an unknown. So you are going to solve from the equations. You are not going to assume that how much is the contact force, but you are going to solve for that.
Yes, sir.
Of course,
Yes, sir.
no, you need some initial guess for the displacements, because this is an iterative solution. So initial guess for the displacements could be, initially all the displacements of all the bodies can be taken as 0. If they're initially gap, so you can displace one body by the amount of gap, so that can be given as initial displacement. So you need that kind of a guess for the initial displacement, which can be taken as 0 actually. So, and if you are using penalty method, then you need, of course, need to check whether the gap is greater than 0 or less than 0. So for that, you initially what your configurations of the bodies are there, we calculate based on that, and subsequently you'll have to update the coordinates by using displacements, and then calculate the gap. So you really don't need the initial value of contact force, but you need the initial guess for the displacements and Lagrange multiplier. Yeah, you may need the initial guess for the Lagrange multiplier also. So the initial guess for the Lagrange multiplier could be, kind of, yeah, the contact normal force. Yeah, you can take something like, if there is a interpenetration, so you can take some contact stiffness and multiply with the interpenetration and get some initial guess for the Lagrange multiplier, or you can also take that as 0 and solve for in the subsequent iterations. Is that okay? Yeah, hello. Yeah, anybody? Any other question? Anybody? Yeah, anybody wants to ask any question, any doubt on whatever we have discussed? Okay, so if there are no questions and doubts, I'm stopping. Thank you all for your attention. Anybody finally any question? So tomorrow's class is going to be the last class, and tomorrow I will be discussing on last topic. So usually in the last deformation or nonlinear problems, we have to trace the equilibrium path. So what we use is what is known as path continuation technique. So I will be briefly discussing about path continuation techniques, and that would be the last lecture. Meantime, you can go through whatever we have discussed, and if you have any doubts and questions, now you can ask. So I'm stopping. Thank you all for your attention. Thank you.